Today we will discuss something on what is known as integration theory or integration. When we started to learn simple arithmetic operations, we started with the very basic thing, that is just addition of two numbers, and then we went on to define and explain some of the complicated concept using those simple concepts. And here also, when we do integration, we have always seen that there is one thing called integrand and another thing with respect to which we are integrating. Now, this operation sometimes looks complicated to understand. So, let us do one thing, let us start or introduce this integration from a very naive notion of functions first. That means, can we define the integration in terms of very simple looking functions. We have already learned that there is one such function which is known as simple function, and it has very nice properties. So, we will try to exploit those properties of simple functions to define, or rather to introduce a sort of first definition of integration of any function. Now, whenever I say any function, we expect that it is already understood that this function should be measurable, and the measurable functions, the definitions of which we have already introduced. So, then we will try to develop the definition of integration based on some more functions, some more general functions, so to say. So, basically we will first introduce the concept of notion of integration using very simple functions in a very simple way, and then from there we will proceed to encompass different types of functions in a very general way. And we will also explore some of the theorems, some of the results that will be extremely useful in deriving many results related to integration and in the area of probability theory. Integration theory. So, let us recap the definition of a simple function, which is an extended real valued function phi on the measure space x script f and mu. Mu is the measure defined on x in script f, is called simple if it is measurable and assumes only a finite number of values, say alpha 1, alpha 2, alpha n, that is phi x equals to alpha I a I x, where a I intersection a j equals to phi. That means, this phi is the null set, that means a I is a disjoint sets, and this is basically x can be written as the disjoint union of sets a I. Now, this is a very important theorem, although very simple. The proof is immediate from the construction. I will discuss in detail the proof. So, first thing is that every extended real valued measurable function f can be considered as a limit of a sequence f n of simple finite valued functions. This is pretty interesting, because whenever you think of any measurable function, obviously that should be extended real valued, then we can think of a sequence of simple finite valued functions whose limit is nothing but our function, original measurable function f. Moreover, if f is non-negative, then each function may be taken as non-negative and the sequence f n may be assumed to be non-decreasing. So, whenever f is non-negative, then we have two additional features, that each of these simple functions can be taken as non-negative and the sequence can be assumed to be non-decreasing. But the most important thing is that whatever measurable function we can think, we can always think that as a limit of a sequence of simple functions. And naturally, from the theorem, as we can understand easily, that it has immense importance in developing or in deriving many theorems related to integration theory. So, let us prove this theorem. So, consider f n x as a particular type of functions where minus n into indicator function over the set f x less than minus n of x, summation I equals to minus n into 2 to the power n to n into 2 to the power n of I minus 1 by 2 to the power n, an indicator function of the set such that f x lies between, that means I minus 1 by 2 to the power n less than equals to f x less than I by 2 to the power n of x, plus I of f of x greater than equals to n x of x. Now, remember these two extreme functions, this defined over f x less than minus n and f x greater than equals to n. This is basically to incorporate the infinite value, the extended real numbers, that means the minus infinity or infinity. So, clearly note that if f x is equals to infinity or minus infinity, this will imply that f n x must be equals to plus n or minus n respectively, which goes to plus infinity or minus infinity respectively as n goes to infinity. And so, this encompasses the infinity situations when f x equals to infinity or minus infinity. And when mod f x is less than infinity, then always we can find some n, and there exists for each n there exists some I such that I minus 1 by 2 to the power n less than equals to f x less than I by 2 to the power n, with I lies between minus n 2 to the power n to n 2 to the power n. And this naturally implies that we can take f n x as I minus 1 by 2 to the power n, because from the middle functions. Clearly, for this choice of f x and f n x, modulus of f n x minus f x less than equals to 1 by 2 to the power n, and this goes to 0 as n goes to infinity. So, clearly f x greater than equals to 0, what does this mean? That means for given any measurable function f, it may be extended real value, that means it may take infinity as well as minus infinity. We can always find a sequence of simple functions f n x such that f n x converges to f x, or f x can be considered as the limit of this sequence of simple functions. Now, consider the second part, that is put a restriction on f x, that f x is non-negative. Then for every n equals to 1, 2 and so on, and for every small x belonging to capital X, we can consider the positive part from this original definition of f n x. That means, f n x now we define as I minus 1 by 2 to the power n, if I minus 1 by 2 to the power n less than equals to f x less than I by 2 to the power n, for I equals to 1, 2 up to n into 2 to the power n, or n if f x greater than equals to n. Again, following the proof just now, that clearly each f n x, f n greater than equals to 0 for every n, it is simple and it is non-decreasing. That means, f n plus 1 x greater than equals to f n x. And moreover, if f x less than infinity, then obviously for some n, f n x minus f x lies between 0 and 1 by 2 to the power n. And f x equals to infinity, then we can choose f n x equals to n for all integer n. So, under both the situations, when f x less than infinity or when f x equals to infinity, f n x goes to f x as n goes to infinity for every x belongs to capital X. So, hence the proof is complete. So, actually you see the proof is pretty obvious and very straightforward, provided we construct f n x in this way. So, now we define, given that simple function, we define integration of phi is a simple function, d mu equals to summation I equals to 1 toward a I mu capital A I. So, we have already seen that in the simple functions definition of simple function. So, it is just a sum of a i's multiplied by the measure defined on capital A I, the set, provided both minus infinity and infinity must not appear in the sum. And if you see somehow that both plus infinity and minus infinity appear in the sum, then we say that the integral does not exist. So, this is the definition of the integral of a simple function. So, there is a very basic definition, and it is just the sum of some quantities, which is quite natural and which actually goes along our notion of the original Riemann integral. We have defined this integration of a simple function. Now, consider one small property, that if phi has a different representation, that means if phi can be written as summation j equals to 1 to s b j mu of b j, then it can be shown that these two representations give the same value, that is summation over I equals to 1 to r a I mu a I equals to summation over j equals to 1 to s b j mu b j. The proof is very simple. We define C I j such that phi equals to double sum C I j I of a I intersection b j, where a I can be written as union of j equals to 1 to s a I intersection b j, and similarly b j is union of I equals to 1 to r union of a I intersection b j, and naturally a I intersection b j are disjoint. In fact, a I is nothing but set of all x such that phi x equals to a I, capital B j is the set of all x such that phi x equals to b j, and from here immediately it is clear that Cij equals to Ai on capital Ai and Bj on capital Bj. Then if we write, so now we can write the integral of the simple function integration phi d mu as a summation over the sets Ai intersection Bj. That means, it would be double sum I equals to 1 to r, j equals to 1 to s, Cij mu of Ai intersection Bj, which is equals to summation I equals to 1 to r Ai and summation j equals to 1 to s mu of Ai intersection Bj. Now, this second sum gives us actually mu of Bj, mu of Ai, because the sum is over j. So, this is summation j equals to 1 to s Bj into mu of capital Bj. Similarly, we can show that integration of phi d mu can be written as just summation I equals to 1 to r Ai and into mu Ai, and hence the result. So, now from this definition of integration based with respect to a simple function, let us consider f to be a non-negative extended real valued measurable function on the measure space x script f mu. Then define integration of f d mu as supremum over phi integration phi d mu, where phi is simple and 0 less than equals to phi less than equals to f. That means, this is kind of we consider a many integrals with respect to many simple functions and just take the supremum, because f is nothing but the upper bound of such functions, all such simple functions phi. So, this way we can define easily as the integration of a non-negative extended real valued measurable function. And note that this immediately reduces to the previous definition if f itself is a simple function. And if we look at carefully that instead of considering a general measure space, if we consider a probability space, then instead of integral sign we usually use expectation sign, that is E, and f in that case is a random variable, and mu is the measure, it is nothing but the probability measure. So, if a random variable x takes finitely many values, then expectation of x is nothing but integration of x dp, which reduces to summation I equals to 1 to r xi probability capital X equals to small xi. It is immediately obvious that the integral of a non-negative Borel measurable function always exists. It may be infinity, but it always exists. That means, it will not be infinity minus infinity. Suppose f is an arbitrary Borel measurable function. So, now our job is to define integration for any arbitrary Borel measurable function. So, let us define f of f plus x, which is maximum of f x and 0. That means, it is equals to f x is f x greater than equals to 0 and it is equals to 0 if f x less than 0. Similarly, we can define f of minus x as maximum of minus f x 0. That means, minus of f x if f x greater than equals to 0 and 0 if f x less than 0. So, f plus is the positive part of f and f minus is the negative part of f. This should be f x less than equals to 0 and f x greater than 0. Now, therefore, we can immediately see that mod of f equals to f plus plus f minus. F can be written as f plus minus f minus, and f plus and f minus, they are all Borel measurable functions. So, now we are in a position to define integration of any arbitrary Borel measurable function in terms of f plus and f minus, and which is in fact integration f plus d mu minus f minus d mu, if this is not of the form as usual infinity minus infinity, and if it is, we say that the integral does not exist. Now, a function f is said to be integrable if and only if integration mod f of d mu less than infinity. That means, it is a finite quantity. So, it is less than infinity. That means, if and only if both integration f plus d mu and integration f minus d mu are both finite. And for any general set A that belongs to script f, we can define integration of f d mu over capital A equals to integration f I A, which is an indicator function of A into d mu. Now, if f is a bounded continuous function from real line to real line, and a mu is the Lebesgue measure defined on the real line, then we can, it is immediately seen that integration of f over the real line with respect to mu agrees with the Riemann integral. So, that means, from Lebesgue integral we can always get the Riemann integral, but integral of f with respect to Lebesgue measure exists for many functions that are not Riemann integrable. That means, it is not necessary that if a function is Lebesgue integrable, it is also Riemann integrable. An example is this: define f x equals to 0 if x is irrational and 1 if f x is rational. So, clearly we can see that upper Riemann integral is b minus a and lower Riemann integral equals to 0. Since upper and lower Riemann integrals are differing from each other, so we can immediately say that the Riemann integral does not exist. Now, mu equals to m. Let us consider mu equals to m, that is Lebesgue measure, and consider this partition a equals to x naught less than x 1 less than up to x n equals to b. Consider the upper Darboux sum, and if we calculate this sum, upper Darboux sum, it is nothing but b minus a, whereas lower Darboux sum is 0. But if we integrate f over the interval a to b with respect to the Lebesgue measure, that is m, we will see we can split this interval a to b into two sets. One is set of irrationals, another is set of rationals. So, it is just 0 the value into the measure of the set of irrationals and plus b minus a into m or the measure of the set of rationals. Now, whatever be the measure of set of irrationals, this value becomes 0 because it is multiplied by 0. On the other hand, Lebesgue measure over the set of rationals always gives us 0. So, finally, the value becomes 0. So, we can integrate this function in the sense of Lebesgue integration, but not in the sense of Riemann integration. So, another interesting theorem that if be a Borel measurable function, then if integration f d mu exists, then for any c belongs to real line, integration c f d mu exists and is equals to c integration f d mu. Obviously, when f is simple, then we can always write this is actually obvious when f is simple. Now, suppose f is not simple, but we can write integration c f d mu equals to nothing but from the definition that supremum over phi integration phi d mu 0 less than equals to phi less than equals to c f, phi is simple, and we assume that f is non negative and c greater than 0. Then immediately we can immediately write c into supremum over psi integration psi d mu, where psi lies between 0 and f, where psi is simple, with the where putting psi equals to phi by c, and so this is nothing but c into integration f d mu. So, when f is non negative, the proof is complete. So, in general we can always write f equals to any Borel measurable function. We have seen that f equals to f plus minus f minus, and c greater than 0 implies c f plus equals to c into f plus, c f minus equals to c into f minus, and so c f equals to c into f plus minus f minus. So, just apply the standard integral integration c f d mu and split this into form of f plus and f minus, and after a little bit of simplification we can immediately get c into integration f d mu. So, this proof is complete, that when it says that if integral f d mu exists, then for any c belong any real number c, integration c f d mu also exists, which is equals to c into integral f d mu, which is actually which matches with the standard notion of our standard integral that we have already done in class 2 level. And again we can write, just motivated by the previous theorem, we can write lots of statements about this Borel measurable integration of Borel measurable functions. Suppose g x greater than equals to f x almost surely, then integration g d mu greater than equals to f d mu. If integration f d mu exists, then modulus of integral f d mu is less than equals to integral of modulus of f d mu. Similarly, if f greater than equals to 0 almost surely and b is a set belonging to script f, then integration over b of f d mu is supremum over phi integration over b phi d mu, where 0 less than equals to phi less than equals to f, phi is simple naturally. If integration d mu f d mu exists, so naturally integration over a f d mu for each a exists, for each a belongs to script f. And if integration f d mu lies between minus infinity and infinity, then minus infinity less than integration over any a belongs to script f of d mu less than infinity. And this, all the proofs follow exactly in the similar fashion as in a, just split them, start writing in terms of the simple functions. You can consider f to be first non negative and then apply its definition, and once you are done with the non negative Borel measurable function f, then consider the general function f as, and we can write f as f plus minus f minus, just apply the definition, we will get all the results. So far we have learned the basic definition of a very simple function, of integration of a very simple function, and then we have extended this definition to encompass how to define integration of any Borel measurable function. We have also seen some of the interesting results related to this integration, these integrations. And one important thing is that during this process we have actually generalized the concept of Riemann integral to introduce what is known as Lebesgue integration. Now, the question is why we should go from Riemann integral to Lebesgue integral. We have already explained that there are some situations where Riemann integral is not really applicable, but in those situations we can apply Lebesgue integral, or Lebesgue integral is very meaningful and we can integrate it, we can get some value of that integral. So, Lebesgue integration is a much more general concept than Riemann integral, and it is with respect to a particular measure. Now, this measure we can define in many ways, anything can be different types of measure we can consider. So, based on that we can define this integration for any Borel measurable function. Obviously, this function should be defined on a probability space, and for which this measure is associated with that space.